Harmonic motion is just motion that can be modeled using periodic behavior. Periodic behavior is just that of an object or a graph that repeats itself between one period and the next, or between one cycle and the next. Say you had a mass, a weight, sitting at the end of a spring, and assume for the moment that that spring is relaxed. That means that this mass is sitting at what we would call its equilibrium. It's in a state of rest. Now let's say that you pull that mass up, or push it up, and release it. Because of the tension in the spring and the mass at the end of the spring, the whole system will drop and then rise again, and then drop and then rise again. It'll just bounce. And in the absence of any friction or air resistance or gravity even, it'll just keep doing that forever. Let's label this axis time, and this one h for height. And height is a function of time. What that means is that at time 0, the spring is resting here. Actually, at time 0, we're going to push it up before we let go. So at time 0, the spring is resting here. When you first let go of it, it immediately drops, and then it swings back up again, and then it drops again. And because there's no gravity or air resistance or anything else, it's going to drop and then rise and then drop and then rise pretty much forever. This is what we call a simple harmonic motion. It's simple because the only thing we're looking at is the motion of the system itself, the initial force applied to it, and then the natural force of gravity working on it, but no external forces other than that makes this a simple system, a simple harmonic motion. Let's repeat the experiment. There's my mass, my weight, and I'm going to attach it to the end of a spring, but this time I'm going to submerge it in water. So now, when I push the mass up and release it, at first, well, it starts here, and at first it does drop, and then it does go up, but it doesn't go up as far because the water is resisting and working against the system. So instead of a cosine looking curve, we might get something that looks like that. Now, I've not done a very good job here. This isn't very smooth, but I hope you get the idea. It still looks like a cosine curve. This looks very much like a cosine curve up here. Well, this one does too, except that something's working against it. Something's preventing the spring or the mass from reaching its full height here. And that's resistance. We call this a damped harmonic motion. We'll be taking a look at damped harmonic motion in the next topic. Right now, we're going to focus on simple harmonic motion. Now, hopefully, this graph looks pretty familiar. It's a cosine graph. We haven't set any of our parameters, so we don't know what the amplitude is. We don't know what our period is. And it certainly looks, if you treat it like a cosine function, as though it has not been moved up or down. It seems to go all the way down to whatever a is. This looks to be negative a, and this is the midline, y equals 0. And it hasn't been shifted to the left or the right either. Now, remember that I labeled the horizontal axis t and the vertical axis h of t, because this is not modeling the position of the spring. The position of the spring is always directly over x equals 0. It's just moving up and down. But at a period in time that is not t equals 0, the spring is going to have some height above or below the x-axis or the t-axis. And so at that given moment in time, we're recording the height. And that's why this graph looks like it does. It's why it's a graph of the height in terms of t, not the position of the spring in and of itself. So with that in mind, we can write the equation of this function as h of t, wrong pen color, h of t is some cosine of t. We've decided that there's no vertical shift and there's no horizontal shift, so I don't need to put a minus c or a minus d. What was it we decided? It was c, wasn't it? There's no minus c in here. All we have to do is figure out what the amplitude is. We've been calling that a. And what the period is. And once we know what the period is, we figure out what k is. Remember that the period is equal to 2 pi over k. And that's pretty much it, with one exception. In this application, we're going to use omega, the Greek letter omega, which looks like a funky W, instead of k. We're still going to call this the period of the function. We're still going to call this the amplitude. In fact, let me make a note that the amplitude is a, and we didn't say this in the previous sections where we're looking at graphs of sines and cosines, but the amplitude is always a positive number because the amplitude is always the distance away from the x-axis, or in this case, the t-axis. Whether you're going above the t-axis or below the t-axis to get to the maximum or the minimum, the distance that you travel is the same. So we'll say that the amplitude is the absolute value of a. Another word for absolute value in this particular context is magnitude, and magnitude essentially just means size. So we're looking at the amplitude being the size of the distance from the t-axis to a maximum or a minimum. There's a new piece of vocabulary here, and that is frequency. If you go back to, look back at your equation here, and remember when we were calling this k, this omega has exactly the same function. It's going to tell us how many cycles this graph goes through between 0 and 2 pi. Let's go ahead and put 2 pi right there for just now. And k, or now omega, is the number of cycles that this graph does between 0 and 2 pi. In this case, it looks like that's going to be 3. So k, or omega, would be 3. The frequency is how many cycles the graph makes per unit of time. So if this is 2 pi seconds, and that's about 6 seconds, right? It's a little more than 6 seconds. Then the frequency is how many cycles per second. So we're looking at, if that's about 6 seconds and there's a total of 3 cycles, then it looks like it's about a half cycle per second. The frequency is a half. In this case, because the value of omega is 3. So what we're going to do is, instead of taking 2 pi and cutting it up into k equal parts, we're going to take the number of cycles and cut it up into 2 pi, because it's 2 pi seconds from 0 to 2 pi, because we're working with time here. It might be minutes, it might be days, but per unit of time, and I'm just using seconds as an example. If I have 2 pi seconds here, I'm interested in how many, what frequency is, what the definition of frequency is how many cycles can I get through in 1 second. Okay, so that's what frequency means. So you have these two formulas. Oh, I need to change that to omega though, don't I, instead of k. These two formulas are just reciprocals of one another. But I don't want you just to memorize the formulas. I want you to think about what these things mean. The period is how long it takes to make 1 cycle. And so the period is the normal amount of time it takes to make 1 cycle, 2 pi, divided by however many cycles there are. There are 3 cycles. There are omega cycles. And the frequency is how many cycles can you get per second, or per year if that's the unit of time, per unit of time. So this is a new vocabulary word for us. These ones are hopefully more familiar. And I hope that you recognize the form that this equation is in as well, as being just what we were working with before when we were learning how to graph sines and cosines, graph transformations specifically, except that the only transformations present here are an amplitude and a k value or an omega value. That's the number of cycles there are between 0 and 2 pi. To look at a quick example, example 1 in your textbook gives the equation for the displacement of a mass suspended by a spring as being modeled by the function y equals 10 times the sine of 4 pi t. All right, so there's my omega t, and they ask us to find the amplitude, the period, and the frequency. Well, the amplitude is just the absolute value of a, and in this case, that's 10. So I'll make a note over here that in this case, our amplitude is 10. Now, we always use we've been using the letter A for amplitude, and we've been putting it in this position. It's important to note that not every textbook and not every application may use A to represent amplitude. They could use a different letter. They could use a capital A. They could use a Greek letter. What matters is what's in the position that our A is in. That value there, that's our amplitude. All right, let's take a look at the period. The period of this function is just 2 pi divided by omega. What is omega? Omega in this case is 4 pi. So now I know my period, or I can compute my period. It's 2 pi over 4 pi, and that's a half. So I was estimating with this graph here. This is not the same graph. I've been given a sine graph to play with here. This is a cosine graph. The amplitude is different. The period turns out to be about the same. And I was just estimating, remember? The period turns out to be the same, but that's coincidental. So the period in this case is 1/2 based on omega being 4 pi. To figure out what the frequency is, I just need to do the opposite. Omega over 2 pi. That's going to be 4 pi over 2 pi. That gives me 2. So here I have a frequency of 2. I can complete 2 cycles in 1 second. The period tells me it takes me half a second to complete 1 cycle. 1 cycle in half a second. 1 second gets me 2 cycles. That's the difference between period and frequency. Let's take a look at this function again. If I rewrite it as y equals 10 times the sine of, I'm going to factor 2 pi out of here. I get 2t, and in fact, I'll just factor the t out on the other end. This is still 4 pi times t. I haven't changed the value of what's inside the parentheses here. But I factored this 2 pi out because it plays such a prevalent role in the period and the frequency. If I factor the 2 pi out, what's left is the frequency. So if I factor out 2 pi, then this is my frequency. So oftentimes, you'll see the formula for either a sine or a cosine for a simple harmonic motion written as not always h of t, but f of t, being equal to a times the sine of 2 pi times v times t. And v is our frequency. If it's in that form, with the 2 pi factored out, then v must be the frequency. That's what we did here. This is a more generic form. All right, let's take a look at how all of this plays out in an example. A mass is attached to the end of a spring. The mass is pulled down from equilibrium, from its resting place, by 15 centimeters and released. The time it takes for one oscillation, that means one cycle, is 14 seconds. Find a model for the motion. Assume no resistance. So we're going to assume there's no air resistance, which of course isn't practical unless you're working in a vacuum, and that there's no medium around the object. It's not sitting in a vat of water or oil or anything like that. I still like to draw a diagram for situations like this. My mass is sitting at rest at first, but before I let it go, I'm going to pull it down 15 centimeters. So this is at negative 15. And then I'll release it. From there, it's going to go up and then down and then up and down. And because there's no resistance, it'll keep doing that forever. Let's go ahead and draw that in. We would have something that looks like this. Now, I've pulled the spring down by 15 centimeters before I begin. That means it's going to go up to 15 centimeters before it drops again. So we're working here with an amplitude of 15. The period is 2 pi over omega, and the frequency is omega over 2 pi. We're trying to write an equation. So we're going to have y equals, that looks to me like a cosine. So I'm going to say cosine for now. My amplitude is 15, and it's a cosine, but instead of starting at the top and coming down, it starts at the bottom and coming up. That's a cosine that's been flipped around the x-axis. So it's negative 15, the cosine of something. Now, remember my generic format for this thing was a times the cosine of, and if I want to, I can write it as 2 pi times, that's supposed to be a v, times t. T is my variable like x, right? Because in this case, I'm doing this over a period of time. So y is a function of t. So I'm going to try writing this as 2 pi times something times t. That something right there, that v, we decided that was frequency. So I'm going to use that here. V is frequency. And if I could figure out what the frequency was, I would just be able to fill in the blank here. Well, I'm given another piece of information in the workup for this problem. The time it takes for one cycle is 14 seconds. So is that frequency or is that period? Remember that frequency was the number of cycles you could get in 1 second, and period was the amount of time it took to do one cycle. We're told here the time it takes to do one cycle. So that's my period. Period is 14. All right, that is 14 equals 2 pi over omega. Now if I multiply both sides by omega and divide both sides by 14, I get this. So my omega value is pi over 7, but that's not my v value, right? I need omega over 2 pi for my v value. Omega over 2 pi is pi over 7 over 2 pi. Let's write that as over 1. Then I can write that as pi over 7 times 1 over 2 pi. Cancel the pi's, and I get 1 over 14. So there are actually a couple of different ways you could write this. Y equals negative 15 times the cosine of 2 pi times v, which is 1 over 14, times t. Or you could take the fact that we now know what omega is. That's my k value, remember? And I can just write that in the position of k or omega. If I do the algebra here, 2 pi times 1 over 14 is 2 pi over 14, which is 1 pi over 7. So I get the same thing here. This value here is the same as this value here. This is a common way to see a function like this written, so that you can just pick the frequency out without having to do the arithmetic or the algebra. But if you're given it this way, you can just say, well, if that's my omega value, then I plug my omega value into this formula, and that gives me the v. It gives me the frequency. Well, my job here was to find a model for the motion, and I've done that. There's one form of the model, and here's another one. Which one is right depends on the scenario. They're both actually right. But which one you might want to use sort of depends on how you're going to use it. In this case, we're doing an exercise in finding a model for the motion, and we've done that. So that's the end of this problem, but I want to use this graph to demonstrate something else. Let's say for the moment that this was your mass at rest, at equilibrium, and that you pushed it up before you started and released it, then it would just go down and up and down and up instead of up and down and up and down. But what if you pushed it up and before you let it go, you gave it a shove? Well, then it's going to start here, but it still only go up so far. So let me show you what I mean by that. You might end up with a graph that looks something like this. And you have an incomplete cycle here of, I'm trying to highlight it, I'm having trouble doing that. Yeah, I have an incomplete cycle here. So in order to kind of balance that out, in order to account for that, you might want to shift the graph over or shift the equation over. In that case, you could have here a minus c. You could have a horizontal shift. It's also possible on occasion that you might have a vertical shift. But those are pretty rare in this case, so I don't want you to worry too much about them, but do be aware that they do come up. There are also a lot of different applications that result in periodic graphs. The brightness of a star, the vibration of a guitar string, what were some of the other ones that your textbook? Alternating current, so electrical engineering, the movement of the tides, even animal populations. There are lots and lots of different disciplines that can use this information graphically and algebraically represented in this way. The thing is, we're not usually working in a vacuum. There usually is at least air resistance. However negligible, it has an effect. I mean, picture yourself standing in front of a spring at the weight at the end of a spring. Pull it down and let it go, and what happens? Sure, it bounces, but eventually, because of air resistance, it stops. And so that's what we call damped harmonic motion, and it has an effect not just on the spring and the system, but on the equation that represents it, the equation that models what's going on in that motion. And that's what we're going to be looking at in the next video.